All right. So welcome along, ladies and gentlemen, to your SETI Institute talk series. Today we're very lucky to be joined by Tom Ditto, the former Tom DeWitt. He did a bachelor's at San Francisco State, a BA, and as a result of the BA, his first two films that he produced were put into the MoMA's permanent and circulating circulation. Then he produced some astronomy-related films, and through his wife, he was introduced to telescopes in an amateur entry point. But then he got funding through NSF for an optical project for a handheld 3D scanner. Then that then led to work with the NASA, the NIAC project, where he was funded to produce a diffractive holographic primary objective telescope that he's going to talk to us about today. And I do also want to mention that Tom is going to be also doing a presentation tomorrow at the Exploratorium. So if you're interested after his talk in some of the films that he's produced, he'll also be showing those as well. So please join me in welcoming Tom.
Okay, thank you, Adrian. Today you'll be introduced to a new telescope architecture. We'll look at the motivation, the new architecture, and conclude with suggestions of how to employ it. Questions and answers will follow along with the announcement of and details about that Exploratorium show. So, as we say, if you looked at the preview screen, you could see that this was coming. This is the architecture of the talk. I want to thank the National Science Foundation and also, of course, NASA for the support they've given me over the course of a decade on this research. And I want to thank my wife, who inspired the whole thing. She's a painter. She painted this tie, and her art is the astronomical type. And I also want to remember my late cousin, Dick Rosenbaum, who was a mayor and a councilman, and also held a PhD from MIT in aeronautical engineering. So he probably would have enjoyed this talk. During the past century, primary objectives grew in size, and that's important because they serve two basic functions. One, they separate stars from each other, and two, they intensify the light of the stars in the galaxies. Both functions are affected by the size of the primary objective, where bigger is better. Images grow brighter and sharper as the primary grows in size. 4 centuries ago, the first telescopes used primaries that were a few centimeters in diameter. Compared to our eyes, this is quite large, and the improved resolution resulted in unexpected discoveries, moons around Jupiter, a ring, or maybe a handle around Saturn. During the past century, as they grew in size significantly, each incremental step doubling mirror diameters took builders twice as long as the prior iteration. I haven't studied costs, but venture that they probably also doubled. As the 10-meter diameter became operational, ambitious astronomers spoke of 50-meter and 100-meter observatories, but goals were quickly revised downward. The enclosure for a 50-meter cost more than the telescope inside, and it didn't really suppress the wind, which is its purpose. And there was no enclosure possible for a 100-meter telescope. It was going to be left out in the opening with a lattice support structure that generated countless diffraction artifacts. There are diffraction artifacts found in almost all mirror telescopes because they are intrinsically coaxial. The focal plane is in the middle of a light path. So here's one, and here is the diffraction pattern. It's a very familiar pattern from an aesthetic point of view. I love it. These diffraction stars that generated by the coaxial method. But if there's an exoplanet in the diffracted light, then it's not so good for optics. Bigger is better, but gravity imposes limitations. The bones of the elephant are at the biological limit for the pillars that can support its quadrupedal mass. An ant can perform what would be Herculean labors at a human scale. SETI understands that small is beautiful. Gravity tugs at the giant Jarrell Bank radio telescope. An array of smaller dishes is a practical solution to the problem of scaling up. Segmented mirrors are one means to grow mirror diameter, but any defect in the mirror surface causes stray light to be sent in all directions. Parabolic mirrors must hold a three-dimensional figure and polish to a level of precision that is a fraction of the wavelengths they reflect. Gravity and inertial forces from motion distort their shape, revealing the edge of segments and scattering light. The blue whale is the largest animal to ever exist. Its buoyancy in water amounts to 0g. Despite its mass, it moves gracefully and swiftly with no gravity. Space deployment ought to permit telescopes larger than those on Earth, just as the whale enjoys 0g in the ocean. But no. Although the effects of gravity are negligible in space, the launch mass to an escape velocity keeps gravity in the equations. The largest space telescope is a fraction of the size of the largest ground telescope. And so it's likely to remain as far into the future as currently planned. The James Webb Space Telescope is 1/5 the diameter of the proposed ground-based 30-meter telescope, yet represents something like 10 times the investment. Mirrors became the default because the prior embodiment of telescopes used lenses. So here you see a 100-foot-long telescope. It's larger in that dimension in some respects than the largest telescopes ever built. But they were ridiculously long. And also, the whole motivation for the length was to repress the inherent chromatic aberration caused by lenses. But the achromatic feature of a telescope brings a trade-off. So here we see the 30-meter mirror modeled. But the trade-off is that the light striking the secondary spectrometers, which are much smaller than the primary, contain no magnification of the spectra that the spectroscopes are supposed to bring out. All the design and power is in an achromatic element, the primary objective mirror. Now look at this. That big mirror is creating a point source, a white light point source. The information astronomers want is in a much larger array of information, the spectrogram. So you can see that the smaller part magnifies the most. There's something out of balance with this fundamentally long-practiced architecture. In describing criteria for improvements in telescope design, Professor Deborah Fisher tells her students, If we keep using the same instruments we've used in the past, we'll get the same results. It's time to design instruments that are fundamentally different. Fisher's spectrograph is an Echelle type, which is fundamentally the same as the design introduced nearly a century ago. It produces high-resolution spectra by cross dispersion and therefore can only see one star at a time. Surveys are extremely important in astronomy because there are billions of objects to map. The Large Synoptic Survey Telescope, LSST, will perform sky surveys, but because of inherent limitations with mirrors, it has no spectrograph. Rather, changes in brightness will be its most important contribution. Kepler and TESS are survey space missions, recording changes in brightness of hundreds of thousands of stars. Neither performs spectroscopy. TESS is a camera, not a telescope. It uses refractive optics, lenses, to maximize field of view. It acquires a 24-degree field of view and trades deep field sensitivity and resolution for complete coverage of a relatively restricted number of very bright stars, looking for exoplanet transit flux attenuation. If any discovery requires spectroscopy, it will be done from the ground, one spectrogram at a time. Spectroscopy is indispensable. Berkeley Optical SETI conducts investigations through thousands of extremely high-resolution spectra. Thousands may sound like a lot of stars, but surveys are in the hundreds of thousands to many billions of stars. Unfortunately, high-resolution spectrograms are not available for almost the entire sky. To collect medium-resolution spectra of galaxies, a specialized robotic system is being readied to plant an optical fiber at the location of each galaxy imaged by a 4-meter parabolic mirror. 5,000 fibers are needed to be positioned dynamically to micron accuracy. Perhaps 35,000 spectra of medium resolution can be obtained in a night of observation. The goal is over 5 years to record the spectra of 35 million stars and galaxies. One problem is knowing where to plant the robotically positioned fibers. For such surveys, a picture is taken first, locating candidates. And then the fibers are lined up in positions to catch the stars that are already mapped in photographic terms. The two-step approach has been practiced by the Sloan Digital Sky Survey with the result that only 1% of the resulting star map has corresponding spectrograms. For a multiple object, fiber-fed spectroscopy telescope such as SDSS and DESI, the Dark Energy Sky Telescope, there is only one spectrum per fiber. So here are the problems that motivated my research. Telescope mirrors are massive. The mirror figure must be perfect. Mirrors have very narrow fields of view. Mirrors do not provide any magnification of spectra. Multiple object spectroscopy is cumbersome with mirror primaries. Mirror telescopes on Earth are much larger than space telescope mirrors. Parabolic mirrors are paraxial, so their secondary receivers diffract light waves. Star maps are required to begin collecting spectrograms. Blind surveys are impossible. Enclosures for mirror telescopes end up costing more than the enclosures themselves do. The fault, dear SETI, is not in our stars, but in our default telescopes. The mirror telescope has not changed in over 3 centuries. The signal reflection has been the default in mirrors. is that they exhibit no chromatic aberration. Isaac Newton wrote the book on optics. He invented a practical mirror telescope which formed an achromatic image. Now, another contribution for which Newton is remembered explored chromatic dispersion. If a monochrome, the sun, is separated out by a first prism, Newton showed that it cannot be reconstituted back into another color by a second prism. First prism, second prism, monochrome. You're wrong, Descartes, he said. In one experiment, he rotated the first prism. Now let's imagine that there are two sources. What happens? After the second prism, two colors are observed at distinct angles in a double dispersion configuration. Multiple sources at multiple angles of incidence can be observed spaced apart from each other by their wavelength. This was my experimentum crucis. Light from a broadband white light sources was diffracted from, so here's the white, diffracted from a secondary, diffracted from a primary diffraction grating, a plane grating, into a lens at a grazing angle where it was focused onto a fiber tip serving as a slit. The diffracted light was delivered by fiber to a spectrometer, and then it was connected by a serial line to the computer so that I could measure the spectrum. I could also measure the available flux with a photometer, and I was able to align the fiber with a little camera. That was my bench. This was my result. Here are three sources. They're separated by a few degrees. A third source exists, separated by the same angular distance, but it's a slightly different lateral position. And if you looked at the spectrometer, the spectrogram that came out of the experiment, you would see that the position of these two sources correspond to two wavelengths, no different than the hypothesis that was shown earlier. And if there's a lateral displacement, if it's in a vertical in this case, the attenuation of the light indicates that it's falling out of view. These scans on the spectrogram are Gaussian curves. Because the light was a spherical wave in the near field, it was not very far away, 3 meters. But I tweaked the laser, I had to find the right wavelength, and it's a plane wave, and it produced a flat spike, showing that a star, which also is a plane wave, provides a plane wave to a primary objective, would produce very sharp spectral lines. No surprise there. What's surprising is that you can tell the angle by the wavelength. An 8-inch primary, the first one was 2 inches, which by the way is a little larger than Newton's first telescope, which is 1.3 inches. So I had a 2-inch first experiment. But the second one I made was an 8-inch membrane. So this is a decorative membrane that I stretched on a frame. Again, I had a lens at a grazing angle and the other features that you saw with the fiber feeding the spectrometer. Now over here is an output of a test of two light sources, and they are vastly different in intensity by 60,000 to 1, almost. So here's the faint one, and here's the bright one. And I had the room lights on when I was running this experiment. You're seeing what the experiment looked like in room light. That's not a flash photograph. The attenuation of the room light was phenomenal. It made jaws drop. There's no background radiations leaking into this very simple system. Now let's apply this to an astronomical telescope. Okay. We have a line of right ascension, a line of stars, east to west on the Earth. So in the center, let's say we look at the center wavelength. It's a plane wave striking a surface. We'll call this is the primary objective grating. It's a plane grating. Light is diffracted off to the side. It's diffracted in all directions, but in the first order, this is the one I'm picking up. It's sent off to a parabolic mirror, B. Another plane wave coming from another angle of the sky at a different wavelength strikes the same grating, and it shares a common axis of reconstruction, this grazing angle. So we have a fixed angle of reconstruction, a fixed receiving angle, call it what you will, with a variation in the incident angle, all the stars in angles across the sky. Now this comports to the basic diffraction equation, where we have a variable angle of incidence, a fixed angle of reconstruction. We have the wavelength lambda and the grating pitch, each groove to groove distance. The integer n is used to be the diffraction order. 0 would cancel the whole thing out, the light would go right through. There are higher orders. I use the first order, so that n is a 1, so it doesn't figure into later equations. But what you see here is that this behavior will conform to one of the most fundamental equations from the 19th century in optics. So if I have various angles of incidence from various sources, I can send them off in a common direction where they're compacted in a common wavefront. If I have a focusing mirror, familiar parabolic mirror off on the side, it can focus that light to a slit, which is the beginning of a spectrometer. So what I've introduced here is a secondary that's a spectrometer to a primary that's a spectrometer, and the result is if I have one particular wavelength that comes out at one particular angle, another particular incident source, pick off that wavelength, it shows up in the secondary spectrometer over here at another angle. You see how this is working? Oh, I can make it, there it works, you see? Okay, well, this is just a drawing, but what do I got? I have a spectrum at the end that is the unique color associated with each angle of incidence of each star in a line of right ascension, the whole arc across the sky that the telescope's pointing at. I'm getting a nod from one understanding person. Well, actually, it's kind of obvious, I think. When you get these spectra, they look like this. Each one of these lines is going to be a particular star at a particular color. Now, if the primary is east-west, the Earth is rotating under it, and a little later in the night, that star shows up at a different color, and then later in the night it shows up at another color. So there's a parade of spectra that you can record one after another, frame time after frame time. I was introduced as a filmmaker. Naturally, I came upon the idea of doing temporal spectroscopy one frame at a time. Well, the resolving power of such a telescope is controlled by the length of the primary objective. If the receiving angle's at grazing, the considerable length of the primary objective is extensible by a power function such that it's possible to model a 100-meter primary that uses a 1-meter secondary parabolic mirror. At 100 meters, the angular resolving power is theoretically 1 milliarc second. In our stellar neighborhood of about 30 light years, habitable exoplanets are seen from Earth as separated from their parent stars by 100 milliarc seconds or so. So I'm exploiting the grazing angle here. I can get very high resolution over the visible bands, for example, as is shown in this plot. And I can have enormous lengths, kilometer lengths, with relatively small secondary parabolic mirrors. I've been writing papers for 12 years, 13 years. They're available here. I can't review the math, the physics in a pep talk, but please take a look at my webpage, 3dwit.com/telly.html. With a 10 meter diameter secondary mirror, which generates 80 square meters, which is true of the Keck, a 10 meters telescope, the primary objective grading collection area runs all the way up to 10,000 square meters. It depends on how you set it up, but the scale is going to be a new world. Since the rotation of the telescope is required to sequence through the spectrum, the platform on Earth can be the Earth itself. Therefore, the scale of the telescope is not constrained by the gimbal platforms that are common with all other telescopes. The gimbal is the Earth. It's a zenith tube of a sort. It's a staring array. But you can rotate it, and I'm showing here with this little axis, that you can rotate the primary objective. So you can see all angles of declination. The whole sky can be obtained. You lock it down for a night, then you can look at another slice of the sky with it. So this is another feature about it, is that because the primary is flat, long ribbon, it's low to the Earth, and some of the characteristic problems of housing telescopes are overcome because the wind pressure is reduced vastly. There's no building. The building all takes place underneath where it's safe in the ground. So it's a peculiar looking instrument, but it is designed for a purpose. These vertical struts suppress a second order so that you have a broader field of view of the sky spectrally. And it has two mirrors, which I'll explain in a second. Now, there's so many stars that it's going to get in a night that I have a luminosity function here, which is sort of a generalized characteristic of how many stars are at any particular magnitude. And it gets to be very interesting above the 15th magnitude, where you can get 27,000 stars in a night. And I'll show shortly, this is sensitive in a very simple version to the 20th magnitude, which means more than 2 million stars a night if you only look at 90 degrees of the sky, which is just part of the night. And your secondary parabola is looking at a 1 degree field of view. So this is a plausible thing. Gratings are ruled on flat surfaces. Grading figure tolerance is highly relaxed, which I'll explain in a minute. The field of view is an entire line of right ascension. Each fiber takes spectra of all objects in the line of right ascension. Spectra are magnified by the considerable length of the primary itself. The deployment in space is not constrained by payload mass or stowage geometry, which I will detail in a minute. Light paths are intrinsically off axis. So there are no artifacts from interstitial structures. It's diffraction free. The basic process is completely spectrographic, allowing blind spectrographic surveys rather than requiring a primary map. And the ground-based version has no wind resistance and does not move during observations. The secondary is buried. Yeah, well, I'm sorry. I just don't have time to go over your many ideas. But no, I've never seen this idea before. I got a Franking when I came out with this idea. That's Professor John Nurlbaum Frank, Jr. Dr. Frank asked, how can a 100-meter plane grating stay flat to an optical figure required of mirrors? It turns out it doesn't need to be. And this is a visual demonstration. I can do the math. It's online. You can see the math. The equations explain, and other engineers have corroborated through subsequent publication, that the flatness tolerance of a diffraction grating, it can be 100,000 times less demanding than for a mirror. So here you see a very wobbly line, which is a reflection of a slit, and here's what comes out of the slit. This is the primary objective grating seen in reflection. This is what comes out of the primary objective grating that's so completely distorted. It's a magic trick? No, it's a simple mathematical study. You got to look at it. I can't go over it here, but you don't have to worry about how flat it is. I would think that solar glint is a major limitation. Have you thought about how sunlight and earthshine is going to be scattered on your detectors? And this came from someone doing exoplanet chronography, and he has that problem. But it doesn't exist here because dust and grooves are almost the same thing. You put a piece of dust on a grating, you don't know it's there because it's just sending the light off in an angle. You're going to lower the resolution slightly, very slightly, from a piece of dust. You will not see glints from edges. A typical frinking is confusion over this telescope and so-called slitless spectroscopy. It's understandable. 100 years ago, astronomers placed diffraction gratings in front of their telescopes in pursuit of multiple object spectroscopy. Unfortunately, where spectra overlap, which is just about everywhere, they could not take any measurements. Similarly, slitless spectrograms suffer from light contamination from background. But Isaac Newton solved this problem 350 years ago. It's called double dispersion. Dr. Frink summarized that the MOST, which is what I call the telescope, would be photon-starved. And he would be right. If the design did not exploit all the light collected by the secondary, David Mazurkiewicz, who helped me with this, was quick to see that the integration times would be far longer than the excursion across one slit if the secondary was fed by a fiber bundle. His sensitivity calculations had a total throughput of 5%, which is quite a lot for an interferometrist like Mazurkiewicz. I show how this figure can be made into 50% by stacking primary objective gratings. Although you shouldn't try multiplying throughput this way with mirrors or lenses. Light comes through, get 1, get 2, get 3, get 4, and every time you build it up, it adds to the total collection. So I go from the nominal 10% efficiency of a grazing angle primary objective grating to 50% just with a stack. But even with its limitations, just one grating, Mazurkiewicz's calculation shows that I can get 10-to-1 signal to noise. Oh, by the way, this is a 1 meter secondary, 100 meter primary. I get a signal to noise 10-to-1 with a resolution of 100,000. The 18th magnitude, I go to a signal to noise of 100-to-1, same spectral resolution, and I drop another magnitude down in sensitivity, and I get 100-to-1 with a resolution of 200,000. The diffraction limit is set by the diameter of the secondary parabola collector and not the length of the primary collector. Well, the opposite is also is the truth, is that the smaller the secondary, the higher the resolution. I demonstrated this mathematically. I demonstrated it in ZMAX. In this particular example, I show a 6-meter mirror is capable of getting 8 thousandths of an angstrom over 20 millimeter slit. So a lot of the light's being lost. The resolution on the sky is 5 milliarc seconds. I go down to 2 milliarc seconds with a 1 meter mirror. And the resolution has gone up, and the allowable slit has opened up to 100 microns, which gives it much more light at the spectrometer. So The opposite applies to the notion that small secondary mirrors control resolution. It's the length of the primary. So, I'm looking at a survey scope that sees the sky, and I'm asking, how good is it relative to other survey telescopes? Figure of merit is omega, which is considered, you just multiply the area of the primary collector times the field of view. So if you have an obscured aperture with that spider and something in it, you've got to take out the light that's blocked. And if you have some telescopes with a triple conjugate where there's a big donut and the primary is much smaller, you really have to deal with that. So that lowers the area for the area parameter. For mine, you just multiply the length times the width, you get the area. And now the question is, what's the field of view? The field of view, as I showed you, was the line of right ascension. That's a very big field of view. That's 180 degrees. There is an overlapping second order that comes out of the horizon. It's blue. And in order to get the whole picture, you have to block it in some way with a filter or something like that. But even if you go to that extra length, extra trouble, you will get at least 100 degrees field of view. So this omega, which is the area, which I've said can be 1,000 square meters or 10,000 square meters, has an area of view which is 100 degrees. So I call, it's a very, very high étendue. The LSST has an étendue of 350 and it's going to break records. This would have an étendue of 10,000 to 100,000 if the areas comport to the potential size of that primary objective grating, and I show here how it can be up to 10,000 meters. If you have, let's say, a Keck as a secondary, it gets huge. So just to review, the performance that this offers is hundreds of thousands of simultaneous spectra in high resolution at very high resolution power, because that's where it takes off. And it's a good survey scope. It sees the whole sky, it collects the whole sky very quickly. So I'm promoting myself here. Dr. Frink, I think you can get at me if you take some notes now. It's not perfect. This is very different than any other telescope, and it has its problems. When I use the grazing angle, I'm sacrificing the efficiency of the grating. So I can increase the grazing angle and get a very long primary objective, but I will lose in efficiency as I do that. So it's kind of a wash. I get a slight increase in the effective collection as I go to a lower and lower grazing angle, closer and closer to the surface of the grating. Okay, so the groove-to-groove spacing tolerance resembles what you suffer with a mirror. You have to grind it to sub-wavelength. Groove-to-groove tolerance has to be sub-wavelength. So making the telescope has the manufacturing nightmare that you've long suffered with mirrors, only it's in a different parameter. It's how accurately are you placing these grooves. And the problem gets worse, as I calculated, as you go into a grazing angle. So it's easier to get a tolerance as you move away from the grating surface. Okay. I can only see as many stars at once as I can resolve in my secondary spectrometer. Current secondary spectrometers are limited. 100,000 is kind of where they work at the top end. They're trying to get to higher. But that is a limit to how many simultaneous objects I can see at any one time. However, in the course of the night, they'll all transit through, so they'll be more than that limit on the spectrometer. In the same way that you can see a very sharp start pattern if you have a secondary lens in your telescope. It's a small lens, but you see a lot of detail. That's also called conservation of étendue. So as you put this telescope in different parts of the planet, it gets different kinds of results. If you look to the North Pole here, you get all night one color. If you look at the equator, you get all the colors, but they fly by very quickly. So where you're pointing is a variable that can interfere with your observational plans. And finally, Dr. Frink, you know, he's raised a conundrum. This is actually David Mazurkowicz, who helped me out, and then he hit me in the stomach. He said, you know, the size of the secondary is really going to limit the integration time. And the calculations are again in my papers and in my report to NIAC. And he's right. If you make the primary objective the same length as the field of view of the grazing secondary, but if you make it much bigger, which you can because it's cheap, then his caveat may not apply. So, and he also went on to say that there were other ways to get around this limitation, but things fly by in a telescope that is looking at the sky in a fixed orientation. You can also get more light through it if you just take advantage of something that's unique. And that is that you can have two mirrors looking at the same primary. Now you've doubled the flux collection. One spectrum goes from blue to red, while the other one goes from red to blue. And they kind of cross in the middle in the green, right? But you get double the flux. And not only that, but in the course of a night, you're getting differential measurements. If there are errors, the difference between the two mirrors will give you your error bar. Differential measurement is a very useful thing in observation, as you know. Now, if you have these mirrors out there and you've decided to deploy it in space, you have inertial platforms, and you can swing the whole thing around to do the scanning like you would a radar. I call it the bolo. And the mass of the secondary collectors provides a lot of the inertial stability. That ribbon is made today for boxes that have spectrographic surfaces on, I don't know, bumper stickers. You see it all the time. This is a factory that makes gratings that are 10 miles long, and this is an earlier version of it. I think they're up to 2 meters now on a roll. I also think it'd be nice if someone mothballed Kodak's film production factory so we could make them with photographic emulsions, which have volume holograms that are much more useful than the kind they make here, which are called surface relief. So when you put this thing in space, what do you have? You have this cylinder that's the diffraction grating, and it can fit in the delivery vehicle very neatly. It might be 10 meters tall. That's a standard thing now. You got a 10-meter tall delivery vehicle. But the diameter of the 100-meter, 200-meter, 1 kilometer is very narrow. So you got your man. This is my man. Sorry, not a good rendering of a man. But here it is, the scale. So that's the guy standing on the bus that's carrying the components that go in the telescope. And here's that man next to it unrolled from that telescope. So you're looking at a 50-meter, in this case, 50-meter by 10-meter primary collector that is a gossamer membrane that's highly tolerant of surface flatness error. It's positioned out in space. It's no longer a problem to get the whale up there to float in 0G. Once it's up there, gravity is no longer a problem in many ways that distort things. My colleague at NIAC, Rob Hoyt, has helped me design the platform for it. He has a 3D printer. This is a spider bot, and it weaves very thin truss work that also is lightweight and is delivered without vibration damage in the initial launch. The two things together could lead to something that looked like this. And I owe it to him for the rendering. There are other ways you can use it on Earth and in space. Unlike Sophia, you can have a completely enclosed primary objective so that the fuselage is pressurized and you do not have this wind factor in a small secondary mirror. Now you have a 10-meter on the roof, on the dorsal side of an aircraft. So I've tried to indicate what that's like, and you fly it through patterns that give you the various integration times and the line of ascension that you need. You can put it on the moon for a lunar observatory, just leave it there, and wait 10 years, you will collect light in high-resolution spectra to the end of the visible universe. Maybe 10 years, maybe 20 years, just leave it there. Get your data back. So that's another embodiment that came to mind. But here's an embodiment that I've been working on the last year or so. There's not time to really cover everything, but while the MOST uses plane grading to magnify spectra and a secondary mirror to focus the concentrated light into a spectrometer, a holographic primary focuses spectra directly. ADEPT takes the very first hologram ever made, the Gabor zone plate, to simultaneously take radial velocity measurements by Doppler shift and at the same time test for a signal that could be expected from an exoplanet that's an Earth twin. ADEPT looks suspiciously like DARPA's canceled Project Moiré. Now, its primary was a version of a Fresnel zone plate. That's very similar. The principal difference between the two telescopes is that while ADEPT is designed to exploit the intrinsic chromatic aberration of diffractive optics, Moiré sought to correct for what it produces and conform a conventional two-dimensional image. The correction limited the bandwidth to, at the most, 40 nanometers. Sometimes it helps to do the very opposite of convention. In the First World War, whenever a biplane went into a tailspin, it was assumed to be doomed. No amount of fighting against the spin with the rudder overcame the fatal spin. One day, a pilot decided to push his stick into the spin instead of against it. His plane suddenly was flying level and straight. The lesson of that discovery suggests that exploiting chromatism of diffractive optics rather than trying to eliminate it provides a correction that we need. So here you have a cross-section made in Zemax of what this Gabor zone plate does. It focuses each wavelength separately onto a rather bizarre image plane that in this rendering looks like a cone. This is a cross-section, so this is a disk. This is a cross-section of a disk. Here's the image plane. And each wavelength of the object that is coming from a plane wave at a very focused point in space is separated. Now, there are lots of other stars, and they're also producing images. And so I calculate all those stars in what are called field angles in Zemax to see how they're going to behave. And what I learn is that they're out of sync with the actual wavelengths I'm interested in, so I can filter them out. This is what the image plane looks like with some fudging that I'll admit to, and I don't have time to explain really how the camera works on that image plane, but it takes advantage of the behavior of diffraction. I can say that I'm getting pretty good point spread functions. Here's the center wavelength, essentially the wavelength that the hologram is made out of, and it performs very well. And as you look to either side, to the blue or the red, you start to see lobes that are acentric. So it's not perfect. But I think it'll be good, especially if I correct it. So here's the image plane itself. And I'm sorry about the quality of my experiment. It was a compact disk. I needed circular diffraction, and that was what I had. I am now in the process of making a real Gabor zone plate. But I did see what I expected, that I would get these rings. They weren't around a cone. They were being recorded on a flat surface, so they're out of focus. But that's okay. They can be very sharp once I get the right image plane. Now let me change just a little bit and talk about some astrophysics that are related to how we look at stars and find exoplanets. If you look at any star, you'll see that even though it's nominally a black body, a white source, it's made up, especially in high energy areas like the blue, of these so-called Fraunhofer lines. They're amplitude shifts that represent such things as the absorption and emission of the atomic particles that are being heated. And the more blue, the more heat and the more energy. And you see these Fraunhofer lines achieving extinction ratios of 50 to 100 to 1 in the near UV and the deep blue. We don't see it with our eyes, but we do see a blue sky. And our blue sky is pretty special. Let's look at our blue sky. If you go around the Earth and you look at the so-called pale blue dot, you will find that in fact it's not pale at all. It's luminescent in the ultraviolet, in the near ultraviolet. So here's the white flux chart shows that the sun is losing energy going into the UV. It starts losing energy around the green, and it keeps going down. But the albedo, the reflection from the Earth, keeps increasing in intensity. It's a differential measurement. It's a gimme. It's a big, fat, 100 nanometer region where there's a spectral change in intensity that says, hey, buddy, you got Rayleigh scattering down there. It's sort of like Earth. It's maybe Earth version 2.0. We don't know. But it is unique compared to all the other planets. I'm evangelizing here, but hey, I haven't had anyone come back to me and say, oh, we've already done that, we checked that, it doesn't work. But it seems to me that if you use our own planets as a reference, the bluest planet, Neptune, dies in the same region. Look at Earth. This is up to 400 nanometers. It's taking off. That's the blue line here. Venus, white, reflecting pretty much what the sun provides, brightly, of course. But at this point, Venus is no brighter than Earth. And of course, Mars has shifted to the red. The real startling thing is that blue planet, and this is also true for Uranus, they do not show Rayleigh scattering. They do not show an increase in flux over the near UV region. I think it's a good signature. Speaking of signatures, or fingerprints, this is the output that you would get from ADEPT, and there's a little moire going on here at the top. That's an artifact of the projection system. I get it over here on my monitor. So I took a slice of it. And you can see that if you have a circular diffraction pattern like I show in moire, okay. Data reduction involves subtracting that from whatever else happens to be there. So if you have two rings slightly rotated by angular differential measurement, then the bright line of the star, once it's subtracted, disappears, and any residuals are coming from something else. ADI is used already, but it's not used on something that is magnified as a spectrum. A spectrum is 1,000 times bigger than the image of the star. This is the fingerprint of an Earth twin in this simulation. It now looks like a moire. It is a moire. It's the interference between the subtraction of those perfectly circular rings and the eccentric off-axis planets, particularly one that's, in this case, blue or ultraviolet, as I've tried to symbolize with the violet colors. So if you see something like this, it's a signal. You've found a planet, and it may have Rayleigh scattering. Okay. I haven't left enough time for questions, with 4 minutes left in a normal talk. Why don't you come to the Exploratorium and have some fun with me? I'm setting up a light show. I'm showing this 1981 video that I made that anticipated long before it was hypothesized by others that a moon could be habitable. I made it blue and green and white, just like Earth, and it's an imaginary moon on an imaginary world, and I was very much into the idea that we would find these exoplanets someday. I also did the work in 3D. And you get free 3D glasses, and there's no charge for admission. The only drawback to going to the Exploratorium right now is Super Bowl City. Okay, I'm going to get the one question at least. All right. Thank you very much.
All right, if you have any questions, then put your hand up and I'll get around to you. It's very fortunate that I have the mic, of course. In 2014, I actually published a paper on spectral bluing of objects in the solar system. So that's obviously right. That's at the basis of your exoplanet detection technique. There weren't actually many places that look as bluing as the Earth, but for example, you do see some spectral bluing, and we've seen with Cassini in the rings of Saturn, for example. And we can talk more about that.
Yes, Dr. Frink, is that a question?
Yes, no, it's a Finkel question, but yeah, I wanted to get that one in.
I will look forward to a conversation on lunch.
Yes. We'll have to go into more depth. I don't see hands yet. Thanks, Cliff.
Hi. So you talked about like placing them in the poles, the equator, the middle, out in space, the moon, et cetera, et cetera. How much will atmospheric distortion affect this kind of telescope? I mean, I know the advantage of an optical telescope going into outer space, but I'm unclear how much, like putting it on a mountain or putting it in a 747 or out in space, how much advantage you get and how much more effective it would be at detecting a potential Earth twin.
Yes, well, of course, if it's an aircraft that's above the waterline, that's an advantage. If it's on the Earth, you're going to have the atmosphere interfering, and that affects LSST because they don't have any way of, in a survey scope of that size, of doing adaptive optics. And this is even worse. So on the ground, you're going to be at seeing. In the sky, in an airplane, you're going to get rid of the waterline and some of the atmosphere. But obviously on the moon and in space, especially in space. So my argument is, why not a bigger one in space? Why are they small? Yeah.
So could you explain again, if you've got multiple stars at a constant right ascension and they've all got different spectra, and you scan across this overnight, how do you untangle which absorption line comes from which star at that wavelength? Or that
yeah, well, you got a clock. Its sidereal time tells you which angle you're getting it from. And the Earth is the big clock. So you know which color is which one. So if you go to the data reduction diagram that I showed earlier, you know what that parade is all about. And it's a nice supercomputer problem because you're going to be getting billions of different little peaks to sort out. But yes, the clock is how you know the longitude. You follow me? Because this is east to west. It's always east to west.
But if you've got two stars in the same right ascension, the blue line from one star is going to land in the same place as the red line from the other star.
Okay, there are two dimensions involved, and it resolves in both dimensions. That's why I showed attenuation in one of the if you have a star that's off axis relative to another star, it attenuates. So they don't interfere with each other in that dimension any worse than they would with the primary of that diameter. So you have a primary that is in one dimension resolving as it normally would, and the other dimension is resolving with a very high resolution that's provided by the primary objective grading. And that's in the one called the MOST. In the one called ADEPT, it's done with filters, and I tried to show you that, but of course there wasn't enough time. Read my papers, please, and write me a letter, please.
It's certainly a very interesting talk. It's unusual in terms of your approach. And of course, everyone has lots of questions as to why does it do this or how does it do that. Do you have an example where you have built a small-scale telescope and operated it and shown its results and its performance?
I did the bench experiment, and I proposed to build one that was a more elaborate bench experiment, and I'm waiting on that outcome. So in NASA you have TRL-1, which is this is, and then you have TRL-2 and TRL-3. TRL-2, it would be a paper study. TRL-3 would be a bench experiment. TRL-4 would take it outdoors. I've designed it to go outdoors. Do you have $500,000? You know, it's a 2-year project with my colleagues, and it'll be outside, and we will do radial velocity measurements of bright stars.
I'm a bit confused. Yeah, I'm a bit confused about the grazing angle. So you've got in your diagram, you had a grating horizontal on the ground. Is the light coming from where's the grazing angle coming from in such a way that you get to use both of your mirrors?
Thank you for your question. It's called Grazing Exodus, and it's not incidence. And people frequently mistake the two, because grazing incidence is widely used in X-ray telescopy. But this is the other way around. If you read my papers, you'll see I do use grazing incidence in a microscope. But you turn it around the other way, and the light shoots off to the side. It's almost at evanescence. Just a little bit. And it can be an evanescence, and it works at evanescence, and that's the lunar version. You know, the light just... Gratings are very different than mirrors. They're very different, and they are off-axis intrinsically. The Gabor zone plate failed because it was on axis. I'm only going to get 1 star out of that.
Any more questions? No? All right, I'll also mention that if you'd like to talk more to Tom, we'll be going to lunch after this, so you can feel free to join us. Tom, we have a special SETI Talks mug. Most of it is black. Hopefully it's not the only thing that you'll be seeing with your non-photon-starved instrument as you build out this outdoor version that we're hearing about in your talk very soon. Please join me in thanking Tom for his great talk.